Hello, hello. We've made it to the one that you've been dreading, maybe, about a quadratic that we actually have to try to interpret what the equation is saying to us. It says that there's this equation, and it can be used to model um, the flight of a rock that has been thrown off of a cliff. Sketch a graph showing key moments in the rock's path. Okay, so what I want to do is I want to graph it first, and we're actually going to draw this graph over here. Ignore that. So many things on one screen. All right. So I'm just going to plug this in. Negative 16x squared. No, not log. Squared. Minus 32x plus 125. We hit graph, and you see something like that. If you don't see that, try hitting zoom and 6. Notice that when you hit zoom, it gives you all these like zoom in, zoom out, zoom to the stats that you put in. Zoom standard is what we're doing right now, because we want the standard window, which is what your calculator automatically does most of the time. And you'll see that you don't see a whole lot. It doesn't even look like a quadratic. People will say, oh, it's just two straight lines. But they're not straight lines. We're just so zoomed in that it looks like they're straight lines. And that is a topic for a whole nother day. But let's work on trying to zoom back out so that we can actually see what we're really looking towards. If you'll notice that my graph that I've given you goes from negative 40 to 160 on the y-axis. So you can actually use that. I don't like to use the zoom in and out features, but if you hit window, it gives you the option to change the x minimum and maximum, as well as the y minimum and maximum. Those are the only four things you'd want to change probably. And I'm just going to make my y values match the y values that you see on the paper. And when I do that and I hit graph, now it looks like a quadratic function. We have all these different points. I think I'm going to amend my previous statement. So we need to figure out like what this is trying to show us. Generally speaking, when you have a situation like something being thrown off of something else, the moment that the function starts to work is that moment where x is equal to 0. So that's the y-intercept. So where does it cross that axis? If you hit second in graph, you'll see that x is 0 when y is equal to 125. And I'm actually going to use all of these points on here to graph the function on my paper. So like 0, 125 would be about right there. Negative 1, 141 would be about right there. There's another point here. You'll see symmetry in this function. So negative 3 and 1 are both 77. 1, 77, negative. Whoops. I'm going a bit too close over here on the left side. Nobody told me, because I'm all by myself. All right, when x is 2, y is negative 3, that's down here, also down here. So the function goes like this. And I'm just using the table. So I graphed it on my calculator, and I used the table to find all these different points. So here's the model or the path of the rock. Okay, it's thrown from a cliff, and I'm going to draw a picture of this cliff. It's thrown down to the water below. Let's put some water here. Here's some water. I imagine there's this person standing here. They have a rock and they throw it down. So actually they throw it down. So how tall is the cliff? That is just the y-intercept. It's the moment that that thing is released and becomes graphable in this function form. So think about it. The function, if the function starts right here, then all this stuff that's back on this part doesn't really make any sense. It's not like if we go backwards in time, we'll see that this rock goes up out of our hand, and then comes back down or something like that. It doesn't make any sense. The actual graph, if we were to show this from the beginning of time, is probably flat line out here where we're just standing there holding it. And then when X is 0, boom, we throw the rock down. So how tall is the cliff? That's the y-intercept, because the moment we throw it, we are throwing it from the top of the cliff. And at that moment, we see that it's 125 feet in the air. Is that 125 feet in the air? And that's that. When will the rock hit the water? That is an x-intercept. That is this point right down here. We know it's just a smidge before 2 seconds, because at 2 seconds we see it's -3. That means it's beneath the water. Second trace 2 is how we find zeros from a previous problem. We know that it's about right here. Now notice the y value isn't 0 right there, which means that this isn't the exact number. If we want that exact number, we're going to have to go left bound or left of that point. So hit the left arrow a couple times, hit enter. Now it says right bound. We have to hit the right arrow key until we're on the right side of that point and hit enter, and then hit enter 1/3 time. We see 1.969 seconds. 1.969 seconds. Hit the water. How high will the rock be in 1 second? Okay, that's just a specific point. If X represents time, then we can hit second and graph. And when X is 1, the rock is 77 feet off the ground. How high will the rock be? 77 feet above the water. Above H2O. When will the rock be 50 feet from the water? This is kind of a tough one. When will the rock be 50 feet from the water? So 50 is not in my table. If I hit the plus sign, I can make my table go by 0.1 if I want, by entering 0.1. And then we might be able to see a little bit closer to when it gets to 50. So sometime between 1.3 and 1.4 seconds. Forget that though. Let's hit y equals. And we can type in, remember y represents the height. So we want a height of 50. That'll give us a second line right at 50. And you see that there's this moment where our quadratic passes through, which models the rock that's being thrown, and then it passes through that 50 at one point. We want to find the intersection. Second trace. We want to find the intersect between those two. And you can kind of scroll over towards that point. You don't have to be very close. Just closer to this point than you are this point. And then we can hit enter 3 times, and it says in 1.385 seconds. 1.385 seconds. All right, average rate of change from 1 to 2 seconds is, rate of change is just kind of a fancy word for slope, but the slope changes. So it's not the true slope between there, but we just want to know how quickly is the rock getting from 1 second, or how much distance is it covering from 1 to 2 seconds. So that's this. So we want to know what's the change in y over the change in x. And the change in y, that would be y2 minus y1 over x2 minus x1. So this is 0.1, this is 0.2. We just want to know the slope between there. That's all. What's the slope? This point is 177. And this point right here is 2, -3. So it goes from -3, or it goes from 77 to -3, and that takes from 1 to 2 seconds. So that is -80 over 1, which is -80. -80 what? Remember these numbers, -3 and 77, those represent feet. And we divided them by time, which was in seconds. So that thing on average was moving 80 feet per second towards the water. And that's what that means. If I give you this one, spoiler alert, it'll probably be a bonus. So I'm a nice person, right? Okay. All right, that's that. I think this is one of the tougher ones, and we're through it.